Hi and welcome to my series on solving the wave, heat and Laplace equations. In this video we'll be solving the heat equation with Dirichlet boundary conditions. It's sometimes also known as the diffusion equation. As prerequisite knowledge you should be familiar with solving first and second order linear ordinary differential equations, and preferably you would have been introduced to partial differential equations before too. But really quickly, I want to draw your attention to the summary sheet that I've made up so that you can spot all the patterns in these equations. As you do a number of examples, you will start to see that these patterns, and you should be able to do most of the workings really quickly or in your head. You'll be able to spot also when you've made a mistake because it won't look like you expect it to. So this here is the case for x equals 0 to x equals L, where L is any finite number. You'll see that we'll be doing the heat equation here. You'll see that our Dirichlet boundary conditions here will have a lambda equals n pi over L for our eigenvalue, where n starts at 1. Because we're doing the Dirichlet boundary condition, we'll also have an eigenfunction x of n that will be a sine function, and it will take the form of n pi x over L. You'll also see that the associated eigenfunction t of n is an exponential function. So just look out for those things. So going back to our heat equation, the first thing we're going to want to do is to interpret what is going on. So for the heat equation here, also known as the diffusion equation, we can pretend here that we've got a solid metal rod here, and with boundaries at x equals 0 and x equals 2 pi. So I'm just getting the 0 from up here and the 2 pi from here. So x goes from 0 to 2 pi. These, by the way, are our boundary conditions, and this is our one initial condition. So you'll see that for the Dirichlet boundary condition, and I'm just going to write DBC for short, it just means, if it's homogeneous, that the temperature on the boundary is fixed to 0 degrees for all time as well. And our U of t here will just be the change of heat with respect to time. I will say change of temp with respect to time. And also D in the equation up here, that is just our diffusivity constant. So each material has its own diffusivity constant. It's just a constant. So I'm just going to be treating it as such. Just be aware that the diffusivity constant D is really easily mixed up with the wave equation for this c squared, because the wave equation looks like this, u of xx. So if you're getting this like in an exam or something, just make sure that you are in fact dealing with the heat equation and not the wave equation, because D may be written as like 3 squared or something. So if it was the wave equation, C would equal 3, but if we're working with the heat equation, D equals 9. So just be aware of that. So that is step 1. Step 2 is to assume solution to the PDE takes the form of u of little x little t equals big X of little x big T of little t. So if we then, so plugging this in to the PDE, this gives us x t prime equals d x double prime t. So step 3, use separation of variables. So I'm just going to write separation of variables. So all that is putting all the t variables on one side of the equation, all the x variables on the other side of the equation. So if we separate it, we're going to end up with something that looks like this. Now, I always write the x's alone by themselves, and any constants or any other variables that you may be dealing with, I put with the t's. And that's simply a matter of habit, so that I'm always working with the same boundary equations. Now this is going to be equal to something k. We don't know what k is, but if x is completely independent of t and t is completely independent of x, which they are, and if they're allowed to freely vary but they still equal each other, we know that k is some constant. Now, instead of writing k, we're actually going to write negative lambda squared. And this is simply because k greater than 0 gives only the trivial solution for Dirichlet and Neumann boundary conditions. So for Dirichlet conditions and Neumann conditions. So that allows me to write negative lambda squared. You may have to prove this for yourself in class, or you can leave that as an exercise for you to do at home. So if we now use this equation here and rearrange it, we can get two ordinary differential equations from our original partial differential equation. So if we rearrange, we get two ordinary differential equations, and they take this form. So I'm just going to draw a line around them because they're important. And I'm going to highlight that step there. Right, so we're going to use this right here for our boundary condition, and we're going to use this right here for our initial condition, because our initial condition is concerned with t and our boundary conditions are concerned with x. So that leads us to step 4. We're going to use the homogeneous boundary conditions. Now, our two boundary conditions should be homogeneous. There is a method to work with if we don't have two homogeneous boundary conditions, but that's for another video. So we're going to be concentrating on this equation here, this ordinary differential equation. Now, you'll see that we don't know what lambda is, but there is two possible scenarios. One is for lambda greater than 0, and we need to consider also the case for lambda equals 0. So we'll start on the left-hand side first. So this is the prerequisite knowledge. So we should know how to solve our ordinary differential equations, especially these linear second order ones. So x double prime plus lambda squared x equals 0. That has a solution in the form of this. X equals a cosine lambda x plus b sine lambda x. And that is where for a and b are constants. But you should write that, but I'm not going to write that just to save time. So now we need to consider our two boundary conditions, and that was for x equals 0 and x equals 2 pi. And both of those conditions should equal 0. So let's chuck in x of 0 here. This is big X here too, and this is little x here. So don't get confused. If you see x in the equation, it's the little x. So x of 0, that's just going to vanish the whole sine function. So we're going to end up with a cosine lambda x, and that all is supposed to equal 0 according to our boundary conditions. So this just implies that a equals 0 here. Now if we put in little x equals 2 pi, we are going to get, remember here that a still equals 0, so we're going to have b sine lambda 2 pi equals 0. Now we could let b equal 0, but if both a and b equal 0, we're going to get the trivial solution. We don't want the trivial solution, so we need sine lambda 2 pi to equal 0, which we know when sine equals 0, so we can write that lambda 2 pi is equal to pi n, where n is some integer. So that will ensure that we get a sine of 0 equals 0. Now if we just solve for lambda, we're going to get pi n over 2 pi, cancel the pi. Now if I just leave that there for a moment and I go over to the right hand side, what I'll do is I'll write for n equals 0, 1, 2 just for now, but we'll come back to this point, and you should remember it from the summary sheet that n will not equal 0 here. So if we consider the lambda equals 0 case, you will see that we get a ordinary differential equation that looks like this, because lambda is 0. And this takes the form, the solution of this takes the form of a little x plus b. This is big X here. And if we plug in our boundary conditions here, so x of 0, that will just equal b equals 0, so b has to equal 0. Now if we plug in x of 2 pi, we're going to end up with a 2 pi equals 0. Now 2 pi won't equal 0, so therefore this implies that a has to equal 0. And if both a and b equals 0, this is just the trivial solution. And the trivial solution is a solution, but it just doesn't tell us anything interesting about what's happening when we're trying to model something. It tells us what's happening when nothing's happening, basically. So we're not interested in it, so we're going to throw those away. You'll see here that our lambda equals n over 2. Here, down here, our n has to start at 1 because our lambda will not equal 0. So hopefully that makes sense. So now we can just write lambda is n over 2 for n equals 1, 2. And that will always be the case for Dirichlet boundary conditions. Your n will always start at 1. So now we can write our x of n. So actually I'll just write, this is our eigenvalue. So that just tells us essentially the values of lambda for when we're not getting the trivial solution, when we're getting some sort of interesting solution. So our x of n equals, sine n over 2x for n equals 1, 2, so on. So I'll put this in green because that is an important one as well. This is called our eigenfunction. So I'll write that next to it as well. Now, step 5. We want to consider the initial condition. Now, our initial condition is non-homogeneous, so there's not a whole lot we can do with it right now, but we just want to get the form that the solution takes. So our, if you remember back to up here, this is the ordinary differential equation we'll be working with. So we'll be working with this ordinary differential equation here. So, all right, this has the solution of the form t of n of little t equals exponential. So again, you should know how to solve these ordinary differential equations here. Minus n squared pi squared dt over L squared. Now, if you recall that L in our particular case, L equals 2 pi, then we can just write this again. Minus n squared dt over 4. So all I did was simplify things. But if I wrote this first one out here, just because you can see back on that summary sheet that I referred to, you'll see the t of n equal this exact thing here. Just like you saw the eigenfunction equal this exact thing up here as well. Right, so I'm going to put a green border around this because, again, this is something that we need. Right. So we can't go any further with this because it's a non-homogeneous condition. What we actually need to do now is step 6, where we just put those two eigenfunctions together. So if you remember at the very beginning, we assumed that the solution of the PDE took this form here. So what we're going to do is just multiply our x of n and t of n together. So our u of n x of t is just going to equal sine n over 2x exponential minus n squared dt over 4, and that is for n equals 1, 2, etc., etc. And I'm also going to throw in a constant here, which I'm just going to call an, but you can call whatever you want. And that is because if x of n and t of n are eigenfunctions, then any multiple of them are also eigenfunctions. So it's still correct if we put this constant in here. So I'm also going to put a green box around this because this, again, is something that is important. And you'll recall where a of n is some constant. Now, step 7. We want to solve for the non-homogeneous initial condition. And if you recall back to the very start here, this was our non-homogeneous initial condition. So I'll just rewrite this again down here. That was u of x naught equals 20 sine 3x over 2. Right, so all we want to do is plug in this here, so when t equals 0 into our u of n. So we have u of n at x equals x and t equals 0. So this just means the whole exponential function just goes to 1. So we just end up with a of n sine n over 2x. And that is equal to what we've got here on this up here. So that's equal to 20 sine 3x over 2. And we can write that simply because this right here and this down here are the same. So now all we want to do is we want to find n, and we also want to find whatever our constant is, a of n. So if we're just matching the left and right hand sides, it's pretty easy here to see that our n should equal 3 because of what's in here and what's there. They match if n will equal 3. They will also match. It's very easy to see that a of n should be 20 here. Sometimes you might get a little bit harder case where you need to do a little bit more rearranging, but that's the general gist of it anyway. Now we can write our specific solution. So step 8, specific solution. That is what we come here for. We have u, and it's no longer u of n because we know what n is now. So it's just u of x of t is equal to, if we go back up here, we just plug in everything that's up here, but we plug in what a of n is and n. So our a of n is 20. So we have 20 sine 3 over 2x exponential minus 9 dt over 4. And that is our solution. So that will model everything that we were presented with in the boundary conditions and the initial condition. So that solves all of those things. Now, just one last thing as we're finishing off. This thing here, it models how the temperature changes in the rod over time between x equals 0 and x equals 2 pi. So you'll notice that for t greater than 0, we have an exponential decay function, so that the temperature will be reducing over time until it reaches a steady state or an equilibrium. So at time t equals 0, all we end up with is a u of x of 0, and it just equals what we had before, so 20 sine 3x over 2. And then you can do t greater than 0. Say if we had t equals 4, then we get u equals 20 sine 3x over 2 exponential minus 9 and times whatever the diffusivity constant is. So you'll see it starts decaying as soon as t is greater than 0. So just to recap what we did, the first thing we did was to interpret and make sense of what the actual question was asking us. you'll see that the Dirichlet boundary conditions are just meant because they were homogeneous, the temperature on the boundary was fixed to 0. For step 2, we assume the solution took the form of big X multiplied by big T, and we plug that into the partial differential equation. And the reason why we assumed this particular solution was because it allows us to use separation of variables. So once we plugged it into the PDE, step 3 was to rearrange that. And we use separation of variables, so we put all the t's on one side, all the x's on another side, and we set it equal to negative lambda squared. And we were allowed to set it equal to that because a k greater than 0 gives only the trivial solution, and we're not interested in that. So we were then able to rearrange what we had for the partial differential equation, and that gave us 2 ordinary differential equations. We used our x variables for the boundary condition, and we used the equation with the t variables in it for the initial conditions. So step 4 was to concentrate on the boundary conditions. We had 2 cases, one where lambda was greater than 0, one where lambda equals 0. We saw that the lambda equals 0 case only had the trivial solution, and this will always be the case for Dirichlet boundary conditions. But we worked through that anyway. The lambda greater than 0 gave us this eigenvalue of lambda equals n over 2. And you'll notice back from that summary sheet that on the summary sheet the eigenvalue was lambda equals n pi over L, where L is our finite number. In here, L equals 2 pi. So you'll see that that was correct. Our eigenvalue also started at n equals 1 simply because the lambda equals 0 case was trivial. So you'll also see that we got the eigenfunction x of n that was a sine function, just like the summary sheet said it would be. Step 5, we then considered the initial condition, so we used that t equation that we saw above. This gave us the general form of an exponential function. We then multiplied our x and our t, our x of n and t of n together, just like we assumed the solution took in the very beginning. This gave us this sort of general form here that satisfied the 2 boundary conditions and would allow us to give some form later on that also satisfied our non-homogeneous initial condition. Step 7 was to solve for the non-homogeneous initial condition using our u of n. So all we did was set t equal to 0 here because that's what our initial condition stated that we needed to do. And then we just solve for our constant a of n and n by equating the left-hand side with the right-hand side of the equation. Then for step 8 was just to write the specific solution, and that was just our u of n up here, but with our a of n and n filled in for our specific solution.